it's a real pleasure to be able to follow such great talks this morning, because a lot of what's been described will make my job a lot easier. So yeah, I'm just wondering, because I've got kind of quite dark slides. Is that better?
Yeah.
People can see that?
Yeah.
Okay, great. So what I wanted to do is really talk into three parts. And in the first part, talk about how to quantify metacognition. So this is perhaps a bit more didactic, a bit more explaining different techniques that we could use if you're interested in quantifying metacognition a lot. And then the second part is going to be more about data, understanding dissociations between metacognition and performance, so some work we've been doing on that. And then the final part is work that we haven't published yet, which is on trying to develop a computational framework for understanding these dissociations that we know exist between performance and metacognitive ability. So I just want to start with kind of addressing a broader question: well, what's so interesting about metacognition? So I noticed in the program that this was meant to be the title of your talk, Chris. I'm not sure if it actually was. I think you had a different title, but I was hoping to kind of recapitulate this title here. And to me, I think one thing I found so interesting about metacognition is that it allows us a formal framework for understanding something that's often quite vague and philosophical, so this idea of reflective awareness. We can kind of build a more formal approach to it, both experimentally and computationally. And as we've heard this morning, this potentially allows us to ask interesting questions about how metacognition operates not just in humans, but also in other animal species. We've just been talking about the work that Sid Kurde is doing on infants, and potentially in the future we might even be doing metacognition studies on artificial intelligence, so who knows. And one of the motivators for my own research is that also we know that metacognition in humans is surprisingly fragile, and it often goes wrong in psychiatric and neurological disorders. And I'm not going to be talking about this so much today, but we've got lines of work looking at metacognitive impairments in various disorders. And this is interesting with the connection with what psychiatrists call insight. So insight in psychiatry is this idea that you have awareness of what's going wrong with you. And these failures of insight have been linked to everything from not adhering to treatment to not seeking help and so on and so forth. But insight in psychiatry is quite a vague concept at the moment, and the hope is that by maybe applying some of the work we're doing in metacognition, we can start understanding insight in a bit more of a rigorous way. So how do we go about studying metacognition? Well, the pioneering work by Fleming and colleagues, as Chris mentioned, was looking at metacognition and memory. And the idea here though was that you're asking a subject to reflect on what's going on in their memory. So perhaps I might think to myself, well, I've learnt enough for an upcoming exam, so I can now stop studying and go down the pub. But that might be a terrible decision to make, right? That might be, then the next day when I'm actually doing the exam, I might have thought, why didn't I study harder? And so this idea that you reflect on the strength of your memory without actually getting any feedback at the time was this kind of more formal approach to the study of subjective awareness of cognitive processes. But this idea, we need to kind of put it against a more historical background. This idea is quite controversial, that we can use these subjective assessments to study anything about introspection. So the history of these kind of ideas about using self-report has been quite checkered. So in the late 19th century, you have people like Wundt and Titchener who were using self-report, an introspective report, as a conduit to the mind, as actual data about the mind. And this was unfortunately shown to be quite unreliable, and so then you had the pendulum swinging over to behaviourism. And the pendulum kind of swung back and forth during the 20th century, so you had papers by Nisbet and Wilson arguing that introspective reports were unreliable, whereas the book by Erickson and Simon was arguing that no, we should use subjective reports about cognition as data. And I think since the late 70s, early 80s, we've now been a kind of in a happy medium here, so where we're not using introspective reports as hard verbatim data on the mind, we're kind of in this middle ground where we're saying we're not going to trust them completely, but we're going to study the process of introspection itself rather than study what introspection can tell us about the mind itself. And this was really picked up on by this article by Nelson and Ahrens that Chris mentioned. So I'll just read out a couple of quotes. So they said that they regarded introspection not as a conduit to the mind, but rather as a source of data to be accounted for by postulated internal processes. And so they treated people as imperfect measuring devices of their own internal processes, and the idea here is that rather than using these reports as data, we're going to study the perfection or imperfection of the measuring device itself. And importantly, they proposed that there's an intimate connection between metacognition and control. Right? So that even if you're imperfectly monitoring yourself, you can use those introspections as input towards the system's behaviour. So more colloquially, if I think that I've learned enough for an exam, I'm going to go down the pub. That's an example of control, even though my introspection might be inaccurate. So in the lab, as we've heard a lot this morning, we can formalise this and say that we're going to use task performance as our objective measure of the accuracy of cognition, and we're going to use confidence as our measure of the metacognitive level, so a second order variable that's related to the task performance itself. And so there's various ways in which you can start to quantify the link between performance and confidence. And I just want to spend a bit of time going through those different measures and thinking about, on a practical level, which are one of the advantages and disadvantages of different types of measures. So let's be a bit more concrete about this. So say we have a task like this. This is a task that we quite often use in the lab. A simple perceptual decision task, similar to the random dot motion task that's been described this morning. Here, we're just asking subjects, it's a brief presentation of two patches of dots, static dots, and the subject just has to say which patch contains more dots. Okay? We could titrate the difficulty of this over time, and then we can then ask the subject to rate their confidence in getting this decision correct. Okay? So how can we quantify the link between their subjective report of confidence and their accuracy on the task? Well, one of the simplest things we could do is simply record every time you were accurate or inaccurate. And so you might have this vector here of ones whenever you made a correct response, zeros whenever you made an error, and we could have another vector of your confidence. Right? So here I'm just thinking of, if we imagine using a binary confidence response here, high and low, then you could just have a vector of your confidence ratings, a 1 whenever you said high confidence, and a 0 whenever you said low confidence. And so intuitively, if you have good metacognition, then you're going to use high confidence when you're correct, and low confidence when you've made an error. And I just flagged up in red here a couple of cases where the subject got it wrong at the metacognitive level. So they were correct here, but they actually rated low confidence. They made an error here, and they actually rated high confidence. Right? So the simplest thing we can do to compute a measure of association here is to just use a correlation. Right? Correlate these two vectors, we get a correlation coefficient between 0 and 1, and we get some kind of measure over many trials of the association between your decision performance and your confidence. And for those of you who know this literature, there's also a related measure called the gamma coefficient, which is very similar to this. Apart from there, you can apply it to confidence scales with just more than 2 levels. Right. Now, part of the problem with this, as a quantitative measure of metacognition, is that it's not independent of your overall level of confidence in the task. So whether you tend to use lots of high confidence or low confidence responses, and it's also not independent of your performance level. So someone who performs the task at, say, 80% correct will tend to, all else being equal, have a higher phi than someone who performs the task at, say, 60% correct. So that might give us cause for concern here, because we're we want to be measuring something about the association between performance and confidence, and not something that's confounded by your performance level or your average confidence level. And so this is just a simulation that I ran. So here I've just simulated a bunch of data where the metacognitive accuracy, so the underlying association between confidence and performance, is constant. But here I'm just showing you that this correlation coefficient, phi, will be predicted to vary as a function of both performance and average confidence, all the way from almost 0 to about 0.6. And so this is kind of like not a good thing if we want to use this as our unbiased objective measure of metacognitive accuracy. And for more details, you can see this nice paper by Mason and Tello, who did a pretty in-depth study of phi and gamma, showing that they're unfortunately confounded by these performance and confidence biases. So what's an alternative? So another approach is to take an approach that's motivated from signal detection theory, which Anne explained to you this morning. And the idea here is that we can compute the separation between the distributions of confidence that you use when you were correct and when you were incorrect. Right, so here we're applying signal detection theory not to the decisions themselves, right, not to the underlying representation of the stimulus, but here we're applying signal detection theory at this second order level. So this is why we call it the type 2 ROC. So the intuition here is that if I were to sort all your confidence ratings and now for this cartoon I'm using a continuous scale of confidence, but it also works using a binary scale. If I were to sort all your confidence ratings for a particular task by whether you were objectively correct or incorrect, then we might see some kind of distributions like this. So when you're correct, you tend to use higher confidence than when you're incorrect. Right? And if you've got good metacognition, then intuitively these distributions are going to be nicely separated out, so you can discriminate your own correct from incorrect trials. Whereas someone else who has poorer metacognition might have distributions that look a bit more like this, so they're overlapping to a greater extent. Now, there's a couple of things about this framework that are useful for us when we're trying to get away from the biases that plague phi and gamma, and that is that this, theoretically, this separation between the distributions is independent of the overall average level of confidence that you use. So in this cartoon I've indicated by this dotted line. So these two hypothetical individuals have the same average level of confidence, but the one on the bottom shows a better metacognitive ability than the one on the top. It's also theoretically independent of your performance on the task. Okay, so there's been nice studies by Sue Galvin and colleagues showing that that is the case in this signal detection frame. And so we can quantify the overlap of these distributions using type 2 ROC analysis. So you're basically computing for every criterion or every confidence level on this scale, you compute the difference in area between these distributions and then construct this curve. Then basically what the idea here is that if there's more separation between these distributions, you're going to get a bigger area under this type 2 ROC. Okay, so the area under the ROC is a measure of dissociation between your confidence and your performance. Now, so this handles the bias problem, by the issue that phi was biased by your average level of confidence, but it doesn't handle the problem that of the confounded performance, right? So for a given level of performance, we know that you're going to have a given area under your type 2 ROC. So another way of saying that is that if you have conditions in which your performance is matched, so you might have two conditions in which you've done pilot work to make sure performance is going to be matched in those two conditions, then you could compare the metacognitive ability in those two conditions by computing the type 2 ROC. But if performance wasn't matched, then we'd be worried that you'd be just getting a bigger type 2 ROC because your performance, your percent correct, happened to be bigger in one condition. than the other. So the final kind of development along these lines for trying to move towards a more unbiased measure of metacognitive ability was introduced by Brian Maniscalco and Hackman Lau, and they came up with this really elegant idea, and they said, well, we know, based on that work by Sue Galvin and colleagues, that this type 2 ROC here, the overlap between these distributions, is in theory dependent on your underlying performance, right? And if we assume a signal detection theory model, then we know that transformation between D prime and your type 2 ROC. So you can go back the other way. You can say, given a type 2 ROC, what's the most likely D prime for that individual, or that condition? And they call that meta D prime. And so you can then compare the D prime implied by your type 2 ROC, or the meta D prime, to the actual D prime in the type. Right? And for an ideal observer, these should be equal by definition. But in practice, you can compute meta D prime on your data, you can compute D prime on your data, you can compare the two, and you can take the ratio, so you can, because these are in the same units, you can compute a measure of metacognitive accuracy controlling for task performance in a particular condition, called meta D prime over D prime. And if that ratio is less than 1, that indicates meta D prime is less than expected based on their performance. And if it's greater than 1, it's better than expected based on their performance, and so on and so forth. And this is, I'll skip this, but basically this is a simulation study showing that it does what it should do.
Steve, can I ask?
Yeah.
So I can understand how you can have, like this ratio can be below 1.
Yeah.
But given the model, how can it be above 1?
Yeah, good question. So I'm gonna, if it's okay, I'll come back to that towards the end, because we're actually, that's a kind of question that's been motivating some of the computational work we've been doing. And so hopefully towards the end it will kind of become clear why that might be. But this is just to show you that in practice, it certainly does be the case that. So here what I've done is, it's relevant to Dan's question, is I've just pulled data from several studies we've run in the lab. So this is about 180 individuals from slightly different perceptual tasks, but basically on all tasks we're able to calculate both D prime and meta D prime. And what you see is that there is a positive association between the two, as there should be, based on the model. But you see also evidence of quite a lot of dissociation. So there's variability in meta D prime that's not accounted for by variability in D prime. And so you see these kind of points down here, and these are what I've just kind of labelled hypo-metacognitive, so meta D prime less than expected based on performance. And this is what you might call hyper-metacognitive, so meta D prime better than expected by performance. And I'm going to come back to why this pattern might exist in the last part of the talk, which is where we start talking about computational frameworks that might be able to handle these dissociations. Okay, so I'll finish this little part, this first part, and then maybe pause for 2 or 3 minutes to see if anyone's got any questions about more practical aspects of how you might measure metacognition. So the idea here is that you need to start with a setting where you can quantify both choice and confidence in the same task on the same trial. Okay? Now, it doesn't necessarily have to be a subjective report. In the human literature, it usually is. But as Armin nicely showed you could use, say, waiting time. I know in their paper they also computed type 2 ROCs, right, in your rat data. So whatever your measure of confidence is, you can use these kind of techniques. And kind of the current recommendations that I'd have is that the type 2 ROC is simple and easy to calculate for most data. We've got some MATLAB code that accompany this review in Frontiers that you might be interested in, and you can apply that to most confidence and performance data. And it might be sufficient if what you want to do is just show, say, differences in metacognition between two conditions where performance is well controlled, or if you're interested in just showing that metacognitive sensitivity is either present or absent. So some people in studies of, say, subliminal perception might be interested in establishing that metacognitive sensitivity is absent. But if your conditions differ in performance, then our recommendation is to use meta D prime, because this allows you to really control for performance across different conditions. The only drawback here is that it does require your task to kind of conform to the signal detection theory assumption. And this is usually okay for most perceptual and memory two-choice scenarios, but if you say you've got a more bespoke task like a target search among distractors or a 10 alternative fourth choice, then you're not going to be able to use this, because you need to be able to categorize your stimuli into two categories. Another potential issue is that estimating meta D prime does require a lot of data. So rather than it being just a parameter you calculate, an ROC parameter, it's a model fit. So you're taking a parameter and you're fitting it to the data. You're also fitting parameters for the criteria, the confidence criteria. So say you have 3 or 4 confidence ratings, you're looking at like 4, 5, 6 free parameters there. And so usually the rule of thumb we use in the lab is that you need about 100 trials per condition, but we've been also working on techniques using hierarchical Bayesian estimation, which the toolbox is kind of in a beta format at the moment, but if you're interested you could drop me an email if you're interested in applying it to your own data. But the nice thing about that is that you can pool data across individuals in a principal fashion and then get, say, a group level estimate of meta D prime, and that's potentially useful for clinical studies as well. And I would say, only use something like phi or gamma as a last resort. So maybe your study doesn't conform to these SDT assumptions, and if you do use it, then I would say be very careful to take a look at bias and performance compounds, because there's a big metacognition literature that has used phi and gamma, and I'd say a large proportion of those studies are unfortunately affected by this problem. And then the other aspect of this is that these different types of measure, they're not only necessarily good or bad, but they also have different interpretations. So recently, Hakon Lau and I wrote this review where we suggested that you can think of really kind of 3 different aspects of your measure. One is what we labelled metacognitive bias, which is a difference in average confidence level despite matched performance. So you might actually be interested in the level of overall confidence, right? Irrespective of underlying correct and error. And this is along the lines of what Dan was talking about. So there you're kind of directly interested in building models of the overall level of confidence and how it's coordinated across individuals. And that potentially is independent of your sensitivities to your own underlying performance. So these are kind of 2 facets. So metacognitive sensitivity we can define as the ability to discriminate between correct and incorrect judgments. You could measure that using the types of ROC. And then finally we can think of metacognitive efficiency as the level of metacognitive sensitivity you have given your underlying performance level. And this could be quantified by this ratio of meta D prime over D prime. And I think this is an interesting development because it now might allow us to compare across, say, patient and control groups or different conditions or different species even, with different levels of performance and different types, and start to kind of say, well, what is the level of efficiency in which a performance level is being converted into metacognitive accuracy. So I wanted to just pause maybe for a couple of minutes and see, are there any questions about the more practical aspects of using these techniques?
This is more general.
Yeah.
But just wonder, so if the sort of the general framework to what extent it can be applied to sort of value-based tasks in which things can be defined in sort of segmentation framework, but the variables are, at least according to economists, are completely different compared to what we are used to use essentially in sort of segmentation theory. Like when we think about value-based, then there's a curvature in utility function and things like that which might affect. But I just wonder, how the framework can deal with sort of both value-based and also sort of motor tasks in which things are again, like the effectors are different.
So I think when you're going, if you're fitting a parameter such as meta D prime, then you're more in the realm of having to make parametric assumptions about how your stimuli are mapped into performance and so on. But I think the type 2 RSC is pretty assumption free in a way. You're just saying computing the sensitivity of confidence given performance. So I think I can't see any reason why that would be a problem for value-based or motor tasks, but I think that the SDT assumptions that underpin meta D prime are probably most secure for perceptual and memory tasks where there's already an extensive literature on single section theory of perceptual memory. For value, we've done a bit of work on value-based confidence, and I know you have as well. And like, it seems as though there's the idea from the economists that you have this kind of point estimates of value is probably not correct, right?
Yeah.
And it might look a bit more signal detection like. But I guess the problem you have in value is defining some objective function. Whereas in perception, you as the experimenter know the right answer.
Exactly.
In value, you don't know the right answer.
Exactly.
Yeah. I mean, it's perhaps worth noting that so these quantities are only independent if they're stable across time.
Mm-hmm.
So if
Yeah.
I'm moving my bias,
Yeah.
that'll affect my sensitivity, metacognitive sensitivity. Because what used to be 4 versus 3 is now 2 versus. Yeah, I can't. You know what I mean?
I know exactly what you mean. And yeah, that's a very good point. And it's, yeah, that is an assumption.
Because it's something I've thought about with the metacognitive efficiency. Because I know they have a paper which I think now it's accepted, where they show, as we've also seen in our data, the sequential effects. You have your past confidence affects your current confidence.
Yep.
And then they showed that this leak, they call it confidence leak, correlates with meta D prime, or D prime, this ratio.
Yep.
But it's really more, in that case, it's more a measure of consistency, whether you are a consistent individual. And I don't know if that ties somehow in with.
No, you're right. Like more generally, just like D prime assumes temporal independence, so does meta D prime. So yeah, there are clearly more fine-grained effects, and like you're showing in your data, it's clearly learning over time based on context. So I don't know exactly how the findings from those new findings that you mentioned fit into that, but it's clearly a issue that I'd imagine it's more of an issue for the kind of studies that you're running with social context and where you're trying to kind of induce learning.
But I will, if I'm, so assume I'm not a consistent person.
Yeah.
But for every moment of time, I'm pretty consistent locally. But then I always change my mind and adopt some new strategy. But then within those moments of time, it'll be high sensitivity, high efficiency. When you look at me across these time windows, I look like I have no idea of what's going on.
Yeah. Yeah.
So, but it's just something to think about also with patience, I suppose.
Yeah. Interesting.
I just have a really small methodological comment, just based on some of my experience with meta D prime, which is, it occurs to me, given the really dramatic individual differences that you and Hakon have shown on the M ratio, that I think maybe when people are preparing to do studies with this, you should inflate your power calculations a little bit. I've noticed, for example, a lot of between subject noise within and across conditions, or maybe it's not noise, but just, you know, subsets of subjects will have almost exact opposite between trial differences and things. And it seems like you should expect that, given that we know people vary quite a lot in their overall metacognitive accuracy.
Yeah, I think that's, I mean, the issue of power and how many trials you need and how many subjects you need to ask, we haven't actually answered that.
It might be interesting to look
properly,
at that.
and we're ongoing work, especially with these Bayesian frameworks, we're trying to do that. So kind of watch this space on power and things like that. Yeah. Okay, so I'm going to move on to the second part of the talk, and I want to move to more empirical work. So we can now use these kind of tools to try and understand associations between metacognition and performance. So how do they arise? How are they related to brain structure and function? And so some of the first work we did on this was using this task that Dan described, where here the subject is asked to make a perceptual discrimination, so in either decide whether the first or the second interval contain a slightly brighter grating, target grating, and then after making this decision, they reported on a 6-point scale how confident they are in their decision. And we recruited 32 subjects across a range of ages and asked them outside the scanner to do 600 trials of this task. And then for each subject, and the other thing I should mention is that throughout this experiment we were titrating using a staircase procedure the difficulty of the task. So we're using a staircase such that if they got 2 consecutive correct answers we make it a bit harder, if they got 1 error then we make it slightly easier, and that allows their performance to settle around a level of about 70% correct per subject. And so what I've done here is show the, for each subject, I've just ordered the subjects by their type 2 ROC area, and by design, their percent correct, their performance in blue here is around 70% correct. But you can see there's quite a wide range of type 2 ROC area. So where 0.5 down here would be almost 0 metacognitive accuracy, and 1 up here somewhere would be perfect metacognitive accuracy. And the other thing to note, so obviously we're controlling the difficulty of the task that underlies this 70% correct, and we also looked at whether there was any association between that and metacognition, and there's also no correlation between the underlying task difficulty and metacognitive accuracy. So this was interesting to us that we seemed to have this parameter that was relatively stable. In other studies we've looked at it across 2 days separated by a week, and you see reasonable stability within an individual. And we wanted to know, well, is there anything about these individuals' brain structure and function that would predict how good they are at introspecting about their performance, as opposed to just the performance itself. So to do that, in this study we used structural MRI scans from the same individuals. So we took a T1 weighted MRI image, extracted out the grey matter volume from that image at each voxel of the brain. We also did a DTI scan, extracted out white matter integrity at each voxel of the brain. So this is fractional anisotropy of the white matter at each voxel. And then we simply entered the fact that these grey matter and white matter values into a multiple regression analysis across individuals to say, is there anywhere in the brain in which greater or lesser grey matter volume or white matter integrity predicted the metacognitive ability. And based on the neuropsychological literature of metacognition, we had prefrontal cortex as an obvious region of interest. And so what we found was that in these, in 2 regions of the anterior prefrontal cortex, so bilaterally, we found that greater grey matter volume there was associated with a greater area under the type 2 ROC. And in the white matter analysis, we found that greater white matter integrity in the anterior corpus callosum, so a region that we know from tractography studies is heavily connected up to the prefrontal cortex, was showing greater white matter integrity in this region in subjects with better metacognitive ability. And importantly, when we looked at any relationship between performance or D prime and the structural parameters in these regions, we didn't see any association. Since we did this study, we've become increasingly interested in the role of the anterior prefrontal cortex, or Brodmann area 10, in metacognition, and there's now convergent evidence from a number of techniques that in humans this region seems to be playing an important role. So we've got studies of grey matter volume, white matter microstructure, both functional activation and functional connectivity of the anterior prefrontal cortex is related to confidence and metacognitive ability. We've also done some studies of looking at metacognitive ability across the lifespan. This is very indirect, obviously, but the idea here is that if metacognition is constrained by prefrontal integrity, then you're going to see a kind of inverted U pattern that follows the functional integrity of the prefrontal cortex, and that's what we see in these 2 studies. So this is interesting because, especially in relation to the comparative work that Armin was mentioning, is that it's interesting, and I completely agree with you that you have these brain structures that are, you have a frontal cortex in a rat, and you have frontal cortex in a monkey and in a human, but the APFC or BA10 is one of these regions which seems to be particularly well developed in humans compared to monkeys. And we know from its connectivity that it's kind of integrating information, integrating inputs from a number of brain regions. And I think the challenge, we're now reaching a stage where we've got convergent evidence on it's playing a role, and now the next challenge going forward is to try and understand what is it actually doing, and what underlying computationally what's happening here to impair metacognition when you impair anterior prefrontal. So one of the studies we've been doing recently, kind of along these lines, is to say, well, okay, most of this work, quantifying metacognitive ability, has looked at simple perceptual decisions, but we know that we can reflect on our performance on memory tasks, on our emotional responses, our physical skills, and to what extent can we think of metacognition as a domain general ability? Is it as simple as just a single hub in the prefrontal cortex that's monitoring ourselves in a homuncular fashion? Probably not. So it was interesting that a few years ago we started thinking about, well, to what extent is the ability, your metacognitive ability on a perceptual task, sharing resources with your metacognitive ability on a memory task? And this was inspired by some early work by my collaborator Hakwan Lau, who's now at UCLA. And what they did was give the same subjects a perceptual task. So here the task was decide whether this low threshold grating is on the right or the left of the screen, and then give a confidence rating in your response, or a memory task. And the memory task was that at the start of the block you had a whole list of words to learn for a limited amount of time, and then on each trial you had to say whether the word on the left or the right of the screen was old on you. And so the idea was to make this also a yes-no task, or a two-choice task, and then that allowed them to compute D prime on the task in the perception of the memory domain, but also meta D prime on each domain for the same subject. And the first thing we looked at was, okay, let's just look at, in these 20 or 25 subjects or so, what's the correlation between metacognitive efficiency on the memory task and metacognitive efficiency on the visual task. So this kind of relates back to the methodological part of the talk, which is that this wouldn't be possible unless you had these kind of tools in which you could normalize performance in the two domains. And they found a significant but pretty non-impressive correlation. And I can say that because Hakwan is a friend of mine. So and there's also these outliers out here, and the kind of story circa 2015 is that having done these studies, we've got another data set that we're working on in functional MRI using these two domains, and the association is sometimes there, sometimes not, depending on the experiment, depending on the study. So if you're a good Bayesian, you'd probably say, well, yeah, there's a weak evidence for a correlation between domains, but there's also plenty of individual variability that's unexplained. It's not as simple as, if you're good at metacognition in one domain, you're going to be good at metacognition in another. And this is kind of supported by their analysis of brain structure. So they also did a very similar VBM analysis to what we did in the 2010 paper. And what they found was that when they put both memory meta D prime and perceptual meta D prime in the same multiple regression model, they found that for perceptual metacognition, the better your perceptual metacognition, the greater the grey matter volume in the anterior prefrontal cortex, in a very similar region to the one that we found in the 2010 paper. But the better your memory metacognition, the greater grey matter volume you have in the medial parietal cortex. And they also did some structural equation modelling on the grey matter volume linked to behaviour, and they found that the best model of the data was actually one in which these contributions, or these associations, were actually relatively domain specific. It's kind of interesting. It's kind of suggesting, okay, the picture is a lot more complicated than I originally thought, even based on these relatively crude VBM measures. we're already getting some kind of evidence from potentially different neural correlates depending on the domain. So we wanted to try and follow up on this. So this was a study we did with patients in New York who had had resection for tumours in the prefrontal cortex. And we managed to recruit a group of 8 patients who had all had resection of the anterior prefrontal cortex, so Brodmann area 10. Now, as is the case with these studies, there was also a lot of heterogeneity in the extent of their lesion. So this is a lesion overlap map. You can see that some patients go all the way back into the frontal cortex posterior to the anterior PFC, but all subjects in the sample had lesions to some part of BA10. Okay. And we also had a control group of patients who had lesions to the temporal lobe for resection to prevent epilepsy. And the kind of obvious question here is, okay, well, if there is domain specificity in meta D prime, then if we might imagine that patients who have lesions to the APFC would be impaired meta D prime in the perceptual task, but perhaps not the memory task. So we used a very similar setup to the one that McCurdy and Hakwan Lau had used. And here we have, the only difference here is that rather than it being a low threshold gradient detection task, which patients really don't like, and well, basically anyone who's not a 20-year-old undergraduate seems not to like, we use a slightly more user-friendly dots discrimination task, the one that I described before. And the memory task was exactly the same as the one in the McCurdy paper. And so what we could then do is for each subject compute their D prime on the perceptual and memory task and their meta D prime on the 2 tasks. And I'm going to show you data from the healthy controls in white, the APFC lesion group in red, and the temporal lobe lesion group in blue. So the first thing to check is just their performance. So here you've got performance on the perception task split by group, performance on the memory task split by group, percent correct on the y-axis. And the first thing to notice is that there's basically all the groups can perform a task. They're performing well above 50% correct, which would be chance performance. And there's no significant differences between the groups in their primary performance and their basic performance. And another kind of subtlety to the perceptual task is that we're also using a staircase procedure here. So we need to look at the average difficulty level of the task that we've had to use to get those subjects to 70% correct. And there's no differences in that parameter, so that's a really slim here. Another thing that we looked at is just, they're rating confidence here on an arbitrary scale, but we just looked at the average confidence level of the subjects on the tasks. And there were also no differences either between tasks or between groups. And so what you can kind of take away from this picture is that if you were to just look at performance on its own or confidence on its own, you wouldn't think there was anything going on here, any problem. But what we're really interested in is the trial-by-trial association between performance and confidence, and that's what we can look at using Metacognition. And so when we do that, we see a pretty interesting pattern. So we see that in the APFC group, there's almost a 50% drop in meta D prime over D prime. So their metacognitive efficiency is decreased compared to controls by about 50%. And it's also significantly below the temporal lobe control group. So this ratio of 1 would be theoretically optimal. And what's interesting is that in the memory task, we don't see any differences between the groups. So there's a significant interaction between domain and group. And so even though we've got small numbers in this sample, we think that this is at least preliminary evidence that there may indeed be domain-specific dissociations here. And one thing that unfortunately we weren't able to do in this study is look at pre- and post-lesion. So that would be a really interesting to do. Colleagues in New York are trying to set that up at the moment, but it's not an easy study to do. But the initial idea is that domain-specific dissociations. Yeah, no, we wouldn't induce the lesion. This is patients who are going to have surgery anyway. Yeah. Okay. So In the last part of the talk, I just wanted to turn now to a more theoretical consideration. So what do the kind of dissociations that I've been talking about here tell us about the computational basis of metacognition? And this was work that I was doing as a postdoc in New York with Nathaniel Dorr. And the starting point for a lot of this work was the notion that if you take a Bayesian view of perception, then, and this is something that came up a little bit in the talks this morning, that whenever you're processing a stimulus, then there's the notion that you kind of have a sense of confidence that comes along with that processing just for free. It's just inherent in the representation of the stimulus. And this is commonly characterized as being some kind of population code, either across time or across neurons, that you have even at the lowest level of sensory representation, so in primary visual cortex, even perhaps the retina, you have some sense of precision associated with that sensory representation. Now this is clearly an important sense of confidence, and we don't yet know how. It's pretty clear that the brain is doing this for early sensory representations, but we don't yet know how it does it. Does it do it using a rate code or a population code, and so on and so forth? And this is clearly an important question. But I think there's often confusion in the field because I don't think this is really what we mean when we think about metacognition. So what I think we mean when we elicit metacognitive confidence in the lab is something higher order. It's rather than some inherent representation of confidence in a sensory representation, which is clearly an important question. It's more at what Chris was calling the personal level. So am I sure that my response was correct? And can I then communicate that to someone else? So I think, and I was trying to think about how does what I'm talking about relate to everything this morning, and I think it relates to Chris's talk quite nicely, because I think the first slide on first order computation is this idea of implicit representation of precision or confidence, whereas this notion of confidence is at the explicit level, and it's second order to some more primary sensory motor pathway. And we could put it in words if say the subject was trying to say what colour the flower is. On the previous slide, the idea would be that you have some kind of population code across colour, and you might have precision associated with that population centred on red, and you could then compute from that representation probability of red given the input, whereas here you might have made the response, or you might be about to make a response, and here would be a higher order notion of am I sure that my response that I'm about to make or I have made to the world is correct or incorrect. So it's more a confidence directed at yourself than confidence inherent to a representation of the world. So how can we start to formalise this idea? And this is something that we've been working on over the past few years, is trying to kind of draw out the distinction between these two notions of confidence. And the kind of idea here is that this second order computation of confidence reflects the probability of yourself being correct, given both the response that you either have made or you will make, and your internal states. And it turns out that the two notions of confidence, first order and second order, are identical only in the special cases where the internal states that support your choice and confidence are identical. So these two notions of confidence are the same, but only in these very limited cases, where the internal states supporting your choices, your responses to the world, and your confidence are identical. So what do I mean by that? Well, we can think of many cases in which they're not identical. So for instance, in a classic task where you're interrogating someone's confidence after they've made a choice, you might have some continued accumulation or continued propagation of internal states, and so if we were to freeze your brain state at the time you made a choice, that might be quite different from the brain state at the time you made a confidence rating. So these states would be dissociable. Similarly, even at a single moment in time, you might have hierarchical readouts of confidence at a lower level, and that's going to induce noise or dissociations between states underpinning choices and states underpinning confidence rating. Or there might be parallel accumulation. And there's lots of combinations of these that might exist Now the important thing that we're suggesting is that we can remain kind of agnostic about where these dissociations come from. We can capture them in a single mathematical framework, which is just the covariance between internal states underpinning your confidence and your choices. And we can then formalize second order confidence as the computation that allows you to go from the confidence state back to the likelihood you're going to be correct in your choice, either backwards or forwards. It doesn't really matter. Well, the idea is that you've just got this inference problem, which is that you've got a state underpinning your confidence representation, and you need to use that state to infer whether you yourself was like to be correct in the task. And so that's what I've just written up here. So given those internal states underpinning your confidence, what's the probability I was correct? This is an inference problem. So there are nice advantages to this when we think empirically, so I haven't got time to step you through all of them, but the idea is that we can then see whether the internal states in the second order computation relate to what we see in real data. And so this is, I'm glad that Armin talks you through some of this, and also Armin talks you through some of this data before. So this is the data from the rat OFC, and it turns out that this kind of X pattern, so where you see a divergence in the firing rate of the OFC as a function of the rat's choice, those internal states are present in second order computation, but they're not present in first order computation. And similarly, we can also recover a sense of error monitoring from the second order model that we can't recover from the first order model. And so the idea here is that in a first order account, confidence is, in a two choice case, is bounded below by 0.5. So the model can never be more confident that it should have done something else than what it actually did. So you kind of, the reason for that is because the confidence is bound up in the representation. So it's not as if it's going to do something else when its representation is telling it to do the other thing. Whereas in the second order case, intuitively, you kind of got an extra view on the problem. You've got a different decision variable that you're using to infer whether your actual responses were correct or incorrect. And so depending on the state of this internal decision variable that's underpinning your confidence, you can simulate things such as errors, objective errors that were either detected or undetected by the model and so on.
How does your model make an error if it knows that it made?
Yeah, exactly.
How does it do that?
So basically, the idea here is that given your response and these internal states that might be decoupled from the internal states.
Why would it make a decision when it's below 50% probability?
So exactly because that these states might be decoupled. That's exactly the reason. So it just happens to be by chance that the decision variable underlying your choice push you one way, but your confidence decision variable is going to push you back.
So in your model you have some temporal part to it?
No, we just have this covariance matrix here.
Ah, okay, so that's where it comes from.
Yeah. Well, it's actually an interesting point that there might be a case where you might want a bit of noise to then monitor your own errors. Right? So that's kind of an interesting thing. Now I can come back finally to this notion of why meta D prime might be above D prime. Right? So this is now not data, this is simulation. But I've just simulated a whole bunch of data sets from the second order model and calculated for each data set their meta D prime and their D prime, and then color coded them according to the model parameters. And basically the idea here is that the model predicts that under some circumstances you will get meta D prime that's greater than D prime. And the reason is, intuitively, that the confidence state has more information than the state underlying the choice. Now this might be in cases where you're under a lot of time pressure, so you're making actions and you don't know what the response is now, but in a few seconds you will know what the right answer was, and so on and so forth. And that's what this is showing here, that the proportion of self-detected errors in the model is, once those get above a reasonable number, then you start getting meta D prime values that are above D prime. So the idea is that in a more general framework we can capture cases of both error monitoring and confidence in the same model, and this might relate to some higher order computation inference on your own models. And it's not just it's not just this is a slide just to say it's not just kind of an exercise in MATLAB. We're using the model to fit real data. So this is work by my student Illy van der Putten, where she developed this task where we can give people a bit of extra evidence after their response before they make their confidence rating, and this induces a dissociation in these two decision variables by design. And then we can then see what basically, as you get more post-decision information, then you get lower confidence when you make an error and greater confidence when you're correct. And this, I'm just putting this up to show that the red lines are fits of the model with just a single free parameter to both performance and confidence. So we're quite happy with the way this is kind of panning out. We're able to fit confidence data recorded from real subjects with just a single free parameter here, both accounting for changes in performance and changes in confidence. Okay, so how long have I got across those? Kind of way over time, right?
Yeah, just carry on.
Just carry on. Okay, so this is the last little bit. So there's also an advantage of placing this kind of framework in a Bayesian setting, and I'm hoping this is going to connect to Dan's talk as well. So I just put this in for a bit of fun. So can anyone tell me? Well, first of all, put your hands up if you see this as depressions going into the screen. Okay. And who sees it as things coming out of the screen? Okay, so mainly depressions. Okay, good. And then who sees this as depressions going into the screen? Okay, and who sees it as bumps coming out of the screen? Okay, the same photograph turned upside down. Right, so I haven't got the animations in this slide, but it's the same photograph turned upside down. And does anyone know what it is?
Rivita or something.
It couldn't be more different from Rivita if I had tried. This is a photograph of sand dunes near the Libyan border with Algeria, photographed by an Italian astronaut from space. And so these are actually bumps so these are all dunes, and you're looking at it from above. And the reason that when you flip the photograph you see it as depressions is that the idea, at least, is that your brain expects light to be coming from above in most settings. So in the outside world you usually have sunlight coming from above, and that's why when you see the sunlight striking these dunes, you see them correctly as bumps coming out. If I flip the photograph, this pattern of shadow is more consistent with depressions going into the screen. So that's just by way of introduction about the importance of these prior beliefs about the structure of the environment. Now, importantly, it's kind of subtle here. It's not a prior belief about seeing dunes or no dunes or Rivita. It's a prior belief about the structure of your visual inputs. Right? So you have, when you're responding to or categorizing the world, you come kind of pre-built or pre-learnt with all these prior beliefs about the structure of your input. Now, it turns out that when you're inferring the confidence that you have in your response, you need priors not about the structure of the world, but you need priors about your own ability. Okay, and in this framework that we've been developing, these priors, I haven't talked much about these priors, but I can just point out that just like priors down here at the perceptual level can cause illusions about the world, priors up here may well cause illusions about yourself. So make yourself think that you're better or worse than you are. And we can simulate this so we can build in different prior beliefs about the parameters of the model and see, and this is similar to the plots that Dan was showing, so the plots of performance against confidence, and we can induce a variety of quotes over or under confidence depending on the prior beliefs at this upper level of the model. And I think it's really interesting. I only started thinking about this morning, but one obvious source for altering these priors is when you're in a social setting. So it could be that, now it's kind of an open question, are you modulating the scale or the usage of the scale, as I was asking Dan this morning, or are you really changing the priors of your ability? I think that's an open question. But one obvious place for it to come in might be kind of an arrow coming in here from your social environment. Okay, so there's also some empirical implications to this model. There should be some kind of common mechanism that underpins both confidence and error monitoring. I haven't gone into this one here, but it turns out that in this inference scheme, the actions that you make themselves carry information about your accuracy. That's kind of a weird one to think about, but it turns out to be a prediction of the model. And also, there's this one here that it turns out that a common computation may, or a common, if you're building a model of how you might infer someone else's confidence, it turns out that you can actually develop a very similar set of equations that you can apply to both inferring someone else's confidence and inferring your own confidence in the second order framework. And there's some studies that have started to kind of come out with support for these implications. So particularly this one up here from Nick Young's lab, showing exactly this, that a common neural signature is covariating both with error monitoring and level of confidence in the response. And I think another link is that in Armin's data, the dopamine responses, that's why I mentioned error monitoring, I think it's actually very consistent. We're certainly not the first people to suggest this. So Axel Clearance has a very similar idea in the neural network literature of a second order network computing a belief about the accuracy of a first order process, and so this is a quite similar in scheme to what we're thinking about. And then finally, this is my last slide. I think the interesting connection for me with self-awareness is this idea that at the first order level, the precision or confidence associated with the sensory representation is somehow hidden in the system, it's encapsulated in the system. Right? Whereas if you're using a higher order representation to infer the accuracy of an output, you're kind of translating that into knowledge for the system. So it's this notion of a higher order belief about the system rather than a precision attached to a representation that's in the system. And this connects to some work in philosophy by Susan Hurley, who pointed out that a minimal requirement for self-awareness might simply be keeping track of both perception and action at the same time. So having a perspective, she says, means in part that what you experience and perceive depends systematically on what you do, as well as vice versa, and that you can keep track of some of the ways in which this is so, even if not in conceptual terms. And I think this kind of notion of inferring not only something about the reliability of the percept, but inferring the reliability of an entire sensory motor pathway is one promising avenue in which we might be able to connect up to a philosophical notion of self-awareness. Okay, so to conclude, I started off by saying that this kind of skeptical introspectionist stance that's been that's grown up since the late 80s now places the scientific study of metacognition on a firm empirical footing. An extension of signal detection theory, so type 2 SDT, allows us to develop things like meta-D prime and quantify metacognition in an unbiased fashion in a range of tasks and domains. I've shown you that individual differences in perceptual metacognitive ability are linked to the structure and function of the anterior prefrontal cortex, although it's now becoming clear that the neural substrates of metacognition in different domains may well differ, and that's a big open question for the future. And our recent theoretical work has been pursuing this line of thought that metacognition may operate as a Bayesian inference on the causes of one's own behaviour. This is potentially separate from the coding of confidence at the sensory level, and that suggests common underpinnings, common computational underpinnings of different behavioural manifestations of metacognition, such as confidence and error monitoring. So I just want to finish by thanking many collaborators, particularly Nathaniel Daw, who's been very, I've worked closely over the past 3 or 4 years to develop the theoretical framework, and thank you very much for your attention.
Any comments and questions?
This is more like a comment. When we think about sort of domain specificity that you were talking about, I think one thing, mainly from sort of a circular standpoint, it is probably also interesting to, even in the perceptual domain only, look and see if different perceptual modalities are working sort of with different brain structures in order to construct the metacognition. So the fact that, for example, there is some in OFC for olfaction doesn't necessarily mean that the same would work for sort of vision.
That's interesting.
Yeah.
We've done a little bit on
another level of essentially sort of
Yeah, I completely agree. We've done a little bit on comparing tasks within the visual domain. So this was work by Chen Song, who works with Garen Reed, showing that if you take two visual tasks, that is contrast detection and orientation discrimination, then even if the performance on those two tasks was uncorrelated across individuals, then their metacognitive ability, their meta V prime, seemed pretty stable actually across the two tasks. So, but yeah, I agree that there's lots of questions about domain specificity that we don't know the answer to.
Just go on.
No, I was very interested in this idea of what the second order can do, which the first order can't do. And I have two comments rather than questions, I guess, but I'd been very interested in the problem of regret, which is wishing that one had done something else. But with your analysis, that can only happen for a second order.
That's right.
Yeah.
That's correct. Yeah.
And
So that would be a form of error monitoring.
Yeah, and which is very interesting. And the other thing, of course, is that you fail to mention Markov blankets.
That's my job.
And
Don't they just keep you warm?
And if the second order system is making inferences about the first order system, as I understand it, there has to be a Markov blanket around the first order system, which something external makes inferences about what it's doing.
Yeah. So that's yeah. Okay. So
It's that that one with the nice eyes.
that's a very interesting point. So the way that this is obviously not very. It's certainly not mechanistic at the level of implementing it with neural networks or anything. The one assumption that we are making is that you have, for a variety of reasons, all of which are kind of shown here, some of which are shown here, you have these two states, and the key assumption is that the state that you have at the time or location at which you're making a confidence judgment does not have access to the state that drove your choices. Because if it did, it would be a trivial problem and it would reduce down to the first order model. I agree.
So I was just thinking, so you know, for example, if I'm a base optimal agent and I have to make some decisions, so there are lots of kinds of noise I should take into account. One of them is perception noise, so we try to isolate all the other factors. So as you said, I should respond to what I see, but you could have tasks in which one response is harder to make than another, or vary the payoff structures where I would make decisions that doesn't necessarily reflect what I believe is the true state of the world.
Yep.
So you might have cases where I shouldn't, it would be up to me to make a decision, even though it doesn't necessarily reflect what I think is the state of the world. And I don't know if that would also be a way of getting at some dissociations.
So then I guess it would come down to what do you find correct?
So am I reporting that I chose what's the probability that my decision maximizes some
right,
utility,
exactly.
something very complex, or does it do a reported probability that my estimate of the world is correct, but which is just only one part of that decision problem?
So that would be, I guess that would be a nice way of dissociating the probability being correct in the sense of maximizing reward and the precision of your sensory state. Yeah, I agree. That would be a nice experiment.
This is more my own confusion. So, given that, you were talking about this sort of confidence signal for free, like in the sort of early visual cortex. The fact that they are there, I wonder if we don't really use them, or if the animal is not really using them. Why they are there? Is it from a brain which is trying to sort of maximize what we can do with the minimum amount of energy? Why that representation is there if it's not useful for proper monitoring of behavior. Do you have any comment on that?
So I think it's important to point out, I'm not saying they're not using them. I'm just saying that in these situations in which you have to monitor perhaps more globally or at a different time point to which you behave, then a lot of these considerations come into play. So the states at which you're using to monitor your performance may well be different from the states that underpin that performance, and then it becomes an inference problem. But yeah, I think that's not to say that they're not being used. So for instance, like in this kind of cartoon, you might well read out the precision of representations here, and then if you apply this scheme, then you might well be really good at metacognition. There's no, it's just a more general framework to say, yes, these representations exist, but it's probably more complicated than just using them directly to report your confidence. And as soon as you have to read something out, or as soon as you have to kind of translate over time, then things, so I think they definitely exist. And another interesting possibility that Chris alluded to in his talk was that we do use them, but we use them implicitly. So in Q combination, so they might be being used all the time, but they might not be being used for explicit monitoring.
Yes. Just a last question, and then we'll bring in some coffee and refreshments.
So I've read some work, this is old work by Shadlin, theoretical, on how a neural network might estimate a value. So if you have, for instance, 10 neurons in your network and you're trying to estimate some value, and then you increase the number of neurons to 20, you've doubled the size of your network. And there's some essentially logarithmic relationship between the number of neurons you add and how well you estimate a value. So the question is, if you see a difference in the size of the frontal cortex, which may have 1 billion neurons, and it may go to 1.1 billion, how much have you really added to its computational ability to resolve a value? I mean, this is of course an oversimplistic view of what the cortex is doing, but this may actually say something about the type of computation that's happening. There are some kinds of computation that might require, 100 million extra neurons.
So I think I should say that the connection between measurements of grey matter volume and what's happening at the level of morphology, and then what the implication for function is really not very well understood at all. So the best guess for what happens when you kind of use these VDM techniques, what you're picking up is dendritic growth. So it's in the cortex, the idea is that you can grow or shrink a brain region, say by learning to juggle or learning to play the piano, and that usually reflects changes in dendritic size, not necessarily more neurons. But beyond that, it's a really indirect link, and the kind of VBM studies I was talking about today were mainly using VBM as a tool to try and kind of carve the structure of the cognitive process, to say, can we pick up dissociation between these two things? What it actually means for the function of the region, and that's a really good question, but not one that we don't know.